All right, good evening. Welcome back to Elements of Calculus 2. We are continuing with applications of differential equations. This is a classic problem for applications of DEs. Okay, so we have a tank containing a mixture of 500 gallons of brine. So it initially has 2 pounds of salt per gallon. So that's we've just got the mixture with all of the stuff in here. So we have, this is 500 liters, or 500 gallons rather. And it is 2 pounds of salt per gallon. So we have 2 pounds of salt per gallon. If I want to figure out how much salt is in this entire mixture, we're going to say we have 2 pounds of salt per gallon times 500 gallons. That's nice. 500 times 2 is equal to, we have 1,000 pounds of salt in this tank. Okay, with the water and it's mixed up. Okay. So that's the first thing to kind of figure out is we have 1,000 pounds of salt in here. You might need this number. You might not. I don't know what's going to happen yet. So what we have is we have a second mixture containing 6 pounds of salt per gallon is added at a rate of 10 gallons per minute. The resulting solution is well mixed. That's an important assumption that we make is that this is mixed up and then drained off at a rate of 10 gallons per minute. So it usually leaves at the same time, uh, rate that it's entering. So we have this is coming in at 10 gallons a minute. This is leaving at 10 gallons per minute. Okay, and we're going to try to figure out how much salt is in here. So let's go ahead. We're going to say let y equal the pounds of salt in the tank. Okay, so what we're going to do is we're going to say, okay, the change in the salt, the change over time, this is equal to, and we'll go ahead and deal with this. We want the concentration moving in, times the rate in, okay, minus the concentration going out times the rate out. Okay, and that's like a very standard setup for a problem like this. Let's put some numbers and some units on this so we could see what's actually going on. Does it make sense that the change of salt is how concentrated it is coming in minus how concentrated it is going out? And then we're just going to figure out how much pounds per salt is going to be coming in and coming out. Again, let's put some numbers and some units on this so we can see what's going on. So we're going to say, okay, I need my change of y over change in t. So what's coming in? We said that it's coming in at, I believe it was 6 pounds per gallon coming in. Okay, so the concentration in is 6 pounds of salt per gallon. So we're going to say 6 lbs per gallon. Okay, times how fast is it coming in? And it looks like it's coming in at 10 gallons per minute. So here we have 10 gallons per minute. Okay, so this is nice because the gallons will cancel. We have 6 pounds. We're adding salt at a rate of 6 pounds per minute. Okay, we're going to do minus. What's the concentration going out? And here's the problem. The concentration is going to be how much salt is in the tank divided by the number of gallons in the tank. So we want salt, the pounds of salt per the number of gallons in the tank. So how much salt's in the tank? And the moment that we turn the system on, you could say, well, doesn't it start at 1,000? Like, yeah, we at time equals 0, but the moment you flick that switch, um, the we don't know exactly how much is in there because this amount is coming in, and we're saying, well, it's the 1,000 times like what tiny amount does this come in, and we don't really know what that is just yet. So we're going to say, you know what? We're going to say, I don't exactly know how many pounds of salt is in. So we're going to say y pounds of salt per that 500 gallons. That's the original concentration that we have in here. And since we know it's just y pounds of salt, this is always going to be the concentration that comes in. And then what's the rate out? And it's going to be leaving at 10 gallons per minute out. So again, my gallons cancel. I have y pounds of salt per minute is leaving. So does it make sense that my change in salt the change of salt over time is 6 pounds per minute going in minus y pounds of salt per minute, 10y over 500. So we can go ahead and make this a little bit simpler, leaving out. But just looking at the units, does that make sense? So we have pounds of salt coming in, or pounds per minute coming in, pounds per minute leaving. So we can have our original setup here. Let's go one step further. So we're going to say dy dt, and we will take a limit in a moment here. So let's go ahead and clean up some of the numbers. So we have 6 times 10, so we have 60 pounds of salt. I'm going to drop off the units for a little bit here because we're just going to work with the ideas here. And then we're going to have 10 divided by 500. So if I was a better person, we could say we would know this is 10 divided by 500. 500. Okay, so we're going to say minus 10 divided by 500, 0 0.2, is it 0 0.2? 0 0.02. Okay, there we go. Let's go back and do this. So 0 0.02, 10, 02 times y. So all I did was take the 10 divided by the 500. And that's what our little abbreviated idea is going to be here. Let's go ahead and take our limit. So I have dy by dt equals 60 minus 0.02 or 0 0.02 y. Let's go ahead and rearrange this a little bit more because if I was doing Euler's method, this would be perfect. We're not going to do Euler's method. We're going to calculate this and we're going to do it with analytics. So let's go ahead and add the 0.02 to both sides. So I have dy by dt plus 0.02y equals 60. Okay. Now this piece here, let's go ahead and replace the dy with just y prime plus 0.02y equals 60. This is a first order linear differential equation. Okay. We could solve this if we only had an integration factor in order to figure out what to multiply this by. Let's get our integration factor. So one of the things for integration factors, it's everything before the y. Okay, and that's how we're going to go ahead and figure this out. Okay, so we're going to go ahead and do that. So I know my integration factor, we're going to do rho. Okay, that's a rho, that's not a p, it's a rho, equals e to the integral of 0.02 dt. Okay, because it's dy by dt, so we have a dt up here. Okay, so we're going to figure that out. So we're going to say rho is equal to e to the 0.02 t, but we have to divide by 0.02, don't we? Because that's how we integrate. Okay, so we go ahead and integrate this piece here. Oh, no, we don't. We're fine. We're just going to say 0.02 t. We're fine. Sorry, I got excited and we did something we didn't need to. Okay, so that's going to be my integration factor for doing all of this. Let's go ahead and see what happens next. So we have multiply this by everybody. Okay, so we have y times e to the 0.02 t plus 0.02 e to the 0.02. Let's go with 0.02. Here we go. Come here. There we go. 0.02t times y. Okay, all we did was multiply by 0.02t equals 60 e to the 0.02t. Okay, now here's the whole point of doing an integration factor is if I put this together, by the way, this is y prime, sorry, I didn't write that down properly. Okay, so we have y prime, and then we're going to go ahead and say this. What this should do for me, adding this integration factor, is saying, well, if I took the derivative of y times e to the 0.02t, what would this derivative be? So you could farm this out to your friends taking calculus 1 and say this is a product rule. So we have derivative of the first, y prime, times the second, okay, plus the first times the derivative of the second. That's going to be 0.02 e to the 0.02t. So if we take this derivative of the first times the second plus the first times the derivative of the second, is this the same thing? And despite the fact that I've changed the order of what's going on here, this is the same idea. So this piece here turns into the derivative of y e to the 0.02t, okay, and this is equal to 60 e to the 0.02t, okay? Now, I want to integrate both sides here, okay? That's what we want to do next, is want to integrate. Fundamental theorem of calculus says we're taking the integral of a derivative. This is just going to turn back into e to the, or y to the 0.02t equals, and then we're going to have 60 e to the 0.02t, but we have to divide by 0.02. We're just, no t down there, sorry. Just get rid of you. Okay, so we're just integrating. This is the formula for integrating. E to the kt, we integrate it, we get 1 over k, e to the kt. That's where this 1 over the 0.02 came from. Okay, we can clean up 60 divided by 0.02. Okay, so we're going to say, great, I've got 60 divided by 0.02 equals, and that's 3,000. So here we have e, or ye to the 0.02t equals, and what did we say that this was? 60 divided by 0.02 is 3,000. 3,000 e to the 0.02t, that took care of that, plus c. Okay, don't forget your constant of integration. It's really important for problems like this. We wanted to solve this in terms of y. So what I'm going to do to both sides here, okay, again, there's a lot of algebra going on here, is multiply it by e to the negative 0.02t. Okay, what's that going to do for me? Y equals 3,000, right? Because that gets rid of this. E to the, well, the exponents are going to add together, aren't they? So this is just going to be a 0. So e to the 0 is just going to be 1. So it's just going to be 3,000 times 1. We don't have to worry about the rest of this. Plus ce to the negative 0.02t. And that's what we have for this. Okay? Now, you're thinking, boy, they gave us a lot of information at the beginning of the problem. We haven't used it yet. This is where we're going to go ahead and use it. So after we have our differential equation solved, we can go back up to the problem description and say, well, when we first started, y is equal to the pounds of salt in the tank. That's why I calculated how much pounds of salt we're going to be in here. They phrase it like we're going to need a concentration, but we don't. Okay, we don't deal with concentrations at all. How much salt did we start with? And it looks like we started with 1,000 pounds of salt in the tank. So when t is equal to 0, t equals 0, there is 1,000 libras, 1,000 pounds of salt in the tank. So we're going to say, here is our 1,000 equals, here's our 3,000 plus CE, and all of this is negative 0.02 times 0, because t is 0. So that's going to be canceled, okay? So we're going to say, great, this is 1,000 equals 3,000 plus C. Well, if I go ahead and subtract off my 3,000, right, we have 1,000 minus 3,000. I'm going to get C is equal to negative 2,000. Okay, so let's go ahead and write down our formula. We have y equals, okay, this is 3,000 minus 2,000 e to the negative 0.02t. And this is what the how much salt I have in the tank at any one particular time goes. Okay, again, if I put t equals 0, this goes away. We have 3,000 minus 2,000, which is going to be 1,000. Perfect. We have a thing going on here. I could ask you a lot of problems after what's going on here. We could say, what happens in the long term? Okay, how much salt in the tank as t goes off to infinity? Okay, so as we think about t going off to infinity, we have e to the negative infinity. That's going to be 0. We're going to have a total amount of 3,000 pounds of salt in the tank. Let me go back to the original problem and see if that makes sense. All right, so we could say, okay, what are we adding here? We are saying that we have 6 pounds of salt per gallon is coming in. How big was the tank? It was 500 gallons. So if you think at the very long range end of this thing, we are adding 6 pounds of salt per gallon and we're going to fill up this 500-gallon tank with this concentration of salt. Does it make sense that 6 times 500 is going to be 3,000 gallons worth of salt in the tank at some particular time? Okay, we're not going to worry about evaporation or anything like that. We're just going to say how much salt. Okay, but there's other questions I could ask you. It's like, okay, how much salt at a particular time? So how much salt after, say, I want to keep the units the same. So we were talking about pounds per minute going in. So we would say, okay, how much salt, say, after 60 minutes? Okay, I can say an hour, but we're going to say 60 minutes for the sake of not making us do unit conversions. And we'd say, okay, well, how much salt is in there? We just say 3,000 minus 2,000 e to the negative zero point zero 0.02 times 60, and we would have to go ahead and figure that out. So we would say, okay, so we have negative zero point zero 0.02 times 60 equals, great, negative 1.2, and say, okay, second function ln. So that's going to be e to the what? E to the negative 1.2. I guess I could have used answer. Okay, equals that times our 2,000. Okay, and then we're just going to say 300, or 3,000 rather, minus that answer I just got. Okay, so after an hour, we're going to have 2,397.6 pounds of salt in the tank. Okay, so we can do that. So I can ask you a whole bunch of questions like how much salt is in the tank after so many hours. But the important thing is we're going to write a function of how much salt is in the tank at any particular time t. Okay, and that's what we would go ahead and deal with this. Okay, so that's how you solve a problem like this. Um, I'll do a couple more of these things, but this is a very, very classic problem. And the way you set this thing up, see, what I want you to remember is going all the way back up to this piece up here is change in Y over change in T. So change in salt is equal to concentration in times rate in minus concentration out times rate out. Remember, the concentration out is going to be your Y over the amount of salt in the tank. So well, I don't know how many pounds of salt, but divided by that. And then we'll go ahead and multiply it by the rate in and the rate out. Okay. And there's things that happen if they're not the same, but usually, especially for the first problem you do with this, the rate in and the rate out should be the same. So you get this kind of a problem to solve. Okay. We can do all sorts of other crazy things to you, but for a first problem, and this is kind of rough, um, this is an appropriate level of a first time you do this problem. Now, you might get two problems on your test. Part A is going, or part one is going to be a problem like this. Part two might be a problem where we do something else with the tank, where we're going to say maybe it's filling up, maybe it's emptying. I don't know. But we will worry about that in a future video. Okay. Thank you very much for watching. Good luck with the test with everything. Good luck studying. Please practice these kinds of problems, and I will see you in the next video. Thank you.